Hi guys, welcome to my homework rewards. Today we're going to work on a question from Statics and Mechanics of Materials, second edition by Hibbeler. It involves adding forces in 3 dimensions. So the question is, determine the magnitude and coordinate direction angles of the resultant force. Why would we want to do this? Well, the resultant force is the total or overall force that would be acting on an object if it was sitting right there at the origin. That would dictate how the object moves. If it was accelerating, for example, if the resultant force was 0, then the object would be in equilibrium. So let's outline some of the steps that we're going to take to solve this problem. We want to find the resultant force, which is the sum of the 2 forces acting on the object. If we want to add forces, which are vectors, it's probably going to be convenient to express them as Cartesian vectors, where we know the magnitude in each direction, x, y, and z. Once we have that, we can add all of the components together to find the resultant vector. And then from there, we can determine the cosine angles. So let's start. Let's label forces F1 and F2. Looking at F1, we have a triangle over here, 7, 24, and 25. This is giving us a similar triangle, which is similar to the triangle made by the 75 Newton force. We can draw that out. This would be Z, the Z component, and this would be Y. So these 2 triangles are similar. They have the same angle, and we can relate them to each other. If we wanted to solve for Z, we can say Z over 75 is equal to the same side on the smaller triangle, which is a 7, divided by 25, which is a hypotenuse. So that if we rearrange this equation, that gives us Z is equal to 21 newtons. You can pause the video now and try to do the exact same methodology to solve for Y. To solve for Y, we're going to write Y over 75. We're using the 75 because we know it, and we only want one unknown in this equation. And we're going to set that equal to 24 divided by 25. 24 is the same part of the triangle on the similar triangle. And when we solve that, we get 72 newtons. So now we know the magnitude of F1 in the y and z direction. So we can actually rewrite F1 as a vector. There is no I component or x component. The y component is actually going in the negative direction. So we should have y as a negative 72.
Hot.
Lost the screen there. Negative 72j. And in the z direction, we have positive 21. So now we've expressed this force, F1, as a Cartesian vector. We know the x, y, and z components. Now we'll do the same for F2, except we have some different information here. We're given a 60-degree and 30-degree angle, but you should note that these are not the direction angles or the cosine angles, because they don't represent the angles from the vector to each of the axes. So instead, we'll start with the z component. You can see that there is a 30-degree angle, which represents a depression from the xy plane. That means that F2z is going to equal 55 times sine of 30. And we're using sine of 30 because that z component down here is opposite to the 30 degrees. Something else that we need to note is this should be a negative, so let's put a negative in front. This ends up being negative 55 over 2. Try to keep everything as fractions, exact numbers till the end, so that you're not rounding. Now, to find the x and y components, we know that there's a 60-degree angle to this line right here, which is on the xy plane. So what we'll do is we'll actually figure out what that vector is. If we know what that vector is, then we know that there's a 60-degree angle to the x-axis. Now, this vector is actually the cosine of the 30 degrees. It's the adjacent portion. What it represents is the scalar projection to that xy plane. So we'll just call this f, and this will be equal to 55 cos 30, which in its exact form will be 55 root 3 over 2. Our friend Wolfram alpha helps us with that one. So now we know the magnitude of that force right there, call it F. And we know that there is a 30-degree angle to the y-axis and a 60-degree to the x-axis. We know that from the x to the y axes is going to be 90 degrees, so we just do 90 minus 60 to give you the 30. So that means that f to x is going to equal f times cosine of 60 degrees. Now, keeping the exact form of f, we end up with 55 root 3 over 4. And f2y is going to equal f cos 30 degrees. And that's going to give us 165 over 4. You might also notice that the y component of this force here is also 60 sine of 60 degrees, because it is opposite to the 60 degrees. So now we have the x, y, and z components. We can write this out. F2 is equal to 55 root 3 over 4i in the positive direction. Also in the positive y direction, 165 over 4j, and a negative 55 over 2k. Now we have f2 and f1 as Cartesian vectors, and we can now start to add them together. So recall that the resultant force is equal to the sum of all the forces. In component form, we have the x component is equal to f1x, f2x. For the y component, f1y plus f2y and in the z component, f1z plus f2z. f1x was 0, and f2x was 55 root 3 over 4. f1y was minus 72. And positive 165 over 4. It's going to give us a minus 123 over 4. And for the z components, we have 21 minus 55 over 2, which is minus 13 over 2. So at this point, we have the components, the x, y, and z components of the resultant force. Putting them all together, we have the magnitude of the resulting force using Pythagorean theorem. Take the x component and square it. Take the y component squared and the z component. This will give you the square root of 1555, which is approximately 39.43 newtons. So what this represents is the overall force that is felt by a point at that object. Next, we want to find the directions. So if you recall, we can find the direction to each axis using cos inverse of the x component over the full force. Trying to avoid rounding, we end up with this, which gives us 53.85 degrees. Try to calculate beta and gamma using the same methodology. For beta, we're going to use cos inverse of the y component over the whole force. This should be a cos inverse over here. This will give us 141.2 degrees. And for gamma, we'll use the z component over the whole force. Which gives us 99.49 degrees. Now we can express the resultant force as a magnitude 39.43 newtons with 3 angles. And these angles represent cosine angles to the respective axes, x, y, and z. And there you have it. We found the Cartesian vectors of each of the forces, added the components in the x and y and z direction so that we could find the resultant force, and then use that information to find the direction cosines. Hope you found this video helpful. If you are looking for a tailored solution and also want to earn rewards while doing your homework, check out MyHomeworkRewards.com and you'll be able to try out other static questions. Thanks, bye.